It's the only answer that's going to give you less than that for the acceleration. And remember, W is mg, right? So that m cancels out essentially. So what's our answer?
C.
Uh, it would be C without the effect of friction. But the friction also affects its acceleration. Okay? So it's gonna be A. C is incorrect. Okay? Oh, she disconnected for a while. Let's just wait. Or is it me? Let's see. Let's see if it... Oh, there she is. There you go.
Hello.
Yeah. Where'd we get cut off?
At the answer is A.
The answer is A. The answer is A. I think, but you got why the answer is A now, right? Because again, if the answer was C, then that means our acceleration is definitely without the the F term here. Okay. So in other words, our answer must be less than g sine theta. And the only answer here less than g sine theta is C for the acceleration.
But to express
Sorry.
yeah, to express acceleration in the formula, we put as n is equal to ma, like F over.
Yeah, because what would happen here if you look here, let's kind of put that in straight away here. So what's gonna be our resultant force here? The resultant force here is equal to W minus F. Well, W sine theta, right? Right? And our F, we know our F is gonna be equal to the actually this part doesn't even need n anymore because we know that F is going to be significant, otherwise it will not be rolling, it will just be slipping, right? So
Yeah.
again, so I'll just put it here since F, let's move it up so it's easier to see. So the resultant force, and that's that equal to MA, and that's going to be equal to W sine theta minus F. Okay? And if
Yeah.
we and then if we put our attention here, we just divide both sides by A. It's gonna be A equals G sine theta minus F over M, right? Now, we can solve this further, but again, we can simply reason it out that this answer, the acceleration here, this is going to be less than G sine theta.
Yeah.
Okay, so I think then from there, we can already guess what the answer is.
Yeah.
Okay. All right. So this is like 4 steps to solve this one problem.
Yeah.
Okay. Yeah, I
Would
know.
you say?
Go ahead.
Sorry. Would you say we can do this in like 2 minutes in the exam?
That's the thing. Okay. I'll be honest with you. 2-step problems. This is what you can do. The easier problems, yes, give yourself like that 1 minute to solve it, right?
Yeah.
All right. For 2 or 3-step problems, or maybe even 4-step problems, give yourself a minute and a half. Okay. So, and then, yeah, that's the only tip I can really give you. The rest of it is you have to really see different points of view on how to solve this. Like in this case, you have to look at torque, and then you have to look at force, right?
Right.
Okay, like remember yesterday again, we had to go through force, and then all of a sudden we had to go through energy and somehow get a term that has mv squared in it, right?
Yeah, exactly.
All right. So these kinds of problems are really meant to be difficult, and these are the ones that will separate those who get 6s from 7s.
Right.
So I have a question, by the way, before we continue. What was your predicted grade before we started learning together?
Probably like 4.
4.
Or
What?
3 even.
3 or
Even
4?
3.
What are you getting now? That's my question.
Now it's a 5,
Ooh.
but like recent exams were quite okay.
Yeah, great. So yeah, if you're really aiming for a 6, we can. But these kinds of problems, if you can get just some of these kinds of questions, you're good for a 6. If you can get most of these, then you're good for a 7.
Right.
All right.
Okay.
So, at the moment, since you're a 5, yeah, it's a good idea for you to just go through these kinds of problems just to get used to thinking 2 steps or 3 steps or 4 steps. Okay.
Mm-hmm.
All right. Um, all right. Let's move to the next question. You have the two masses connected by a rod of negligible mass, and they're rotating around the same vertical axis. Okay. You're given the ratio. Here's the problem. You're given the ratio. Um, Okay, let's see. They're given the ratio that the big M is what? Uh, oh, the distance between the masses is 1 is to 2, right? So the smaller mass is twice. What is the moment of inertia? All right, this one is more straightforward. Okay. Moment of inertia by definition. And this time I'm gonna avoid the word, the letter L because of the letter L here, right? I'm gonna use the word
Mm-hmm.
for now. So moment of inertia. Um, by definition, this is just the sum of m times r squared, where r, okay, where r would be the distance from the turning point or the pivot, okay.
Okay.
Okay, and since you're gonna do sums, you're gonna have to take into account both the actual mass and the individual distances. You cannot use the full distance. Okay, but here's the deal as well. You're told that the distance between these is 1 is to 2. So this is gonna be 1. That's gonna be x. Let's just say x right here. This is gonna be 2x, right? So in this case, you can see that L is equal to 3x, and therefore x is simply L over 3. Okay. All right.
Yes.
Okay. I think I'll change letters as well just to reduce confusion. I'm gonna change that X to R. Okay. Just to avoid confusion. But I think you get the point either way, right?
Yeah.
Okay. So one more change there and there. Okay. So this is R. This is 2R. So that's gonna be 3R. So R is equal to L over 3. Now that we have that, we are going to do moment of inertia problem now. So we're gonna put that into the definition. Okay, so that's going to be equal to big M times R, right? Plus small m times 2R. But we're gonna change the R now into L. So that's going to be M big M L over 3 plus small m times 2L over 3. So we can factor out the L over 3, right?
All right.
Okay, factoring that out, we get 2, sorry, not 2, L over 3 times M plus 2M. That's our final answer. Do we have a choice like that right now? What was D?
Oh.
Oh, sorry, I forgot. I forgot that should be squared. So I have to square that. Sorry, my mistake on that. So I have to
All
square
right.
this as well, right? So we're left with L squared over 9 here. So that's it though, but here we get 4, not 2. So let's do that quick correction. So now that we have that, let's see which one has the choice. I also don't have the full screenshot, I think. Oh,
Yeah, I'm
okay.
sorry. I'll
Don't
look
worry.
at it.
Okay, I think either way, D is not the answer. We already can kind of guess what the answer is. No, we don't even have to
B.
guess. We have the actual answer.
Yeah. It's over
Right?
9.
It's B. Okay.
Yeah.
All right. Um. Okay. I have an idea. Just thinking about it earlier, I have an idea. Later on, once you get used to these three or four step questions with the long way to solve it, and we have time, I hope we have time, we can revisit some of these questions but do a shorter version. Okay.
Okay,
All right, but
perfect.
for now, let's do the long way first so you can get the ideas. Okay. All right.
Yeah.
Let's take a look at the next question. First, in this case, you have a radio placed on a turntable. Um, okay. Yeah, the turntable rotates anti-clockwise with a constant angular frequency. The frequency of the generated sound waves, F, like that. Frequency of the sound waves is determined by a detector, and that's what the detector says. The diagram shows four possible starting points for the radio. Okay, now this is Doppler effect. Okay. Okay. Now you know that for the Doppler effect, let's write that down first. For the Doppler effect, approach means F prime is greater than F, right?
Yeah.
Okay. And similarly for if it recedes, that is the other way around. F prime is less than F, right? If you have neither of these, then F prime equals F, right? So this is the key idea. Of course, the equations tell us what the actual values would be, but this is always going to be the key idea. Okay. So let's take a look here at this point. At t equals 0, what is F compared to F prime? So at
Smaller.
t equals 0, F prime, look, that's the equilibrium position of the wave, so to speak, right? So in this
Yeah.
case, it's gonna be equal to F. Okay, that already tells you that. Now, at this point, t1, at t equals t1, what happens here? F prime is less than, other way, less than is gonna be like that, right? So this should be enough for you to tell, this should be enough to tell you what is happening here at t1. Is it receding or is it approaching?
Receding.
It's receding, it's going backwards. So remember that. Okay, let's look at this now. We don't even have to look at the rest. Let's take a look here. Which of these 4 points is the motion going away or receding from the detector? Now I'm just drawing the 4 velocity arrows for each of these individually, right? So A, is it receding, approaching, or neither?
Neither.
It's neither, right? So neither. For B, what's happening?
Oh, it's receding.
Recede. Okay, we don't even have to do the rest because we have exactly what we want. It should be neither then recede. So what is our starting point?
Um,
Again, from here we go from neither to receding, right?
yeah.
Okay.
But we have to pick one of the points.
Okay, which of the 2 points do you have to pick from now? Which 2 points?
A and B.
A and B now, right? Now, here's the thing though. The question is, where does it start? At t equals 0. In other words, we're looking here.
Right. So it's A.
It's A. All right, so it's now A. Great. Okay, so this is now, we don't have to use the formulas. We just have to reason it out.
Okay.
Okay. Questions?
No, it's clear.
All right. Hold on. The next problem you have here is not really an IB question, but I can see this is somewhat introductory university level, I think,
Oh.
which is about as difficult as IBDP, right?
I think it's from Sulcos, probably.
Yeah.
The prediction, the
Mm-hmm.
for the IB exams.
All right. Yeah. Well, okay. Just so you know, I am in a Facebook group with him about with
Right?
all the DP teachers. So I don't really know him, but at least I'm connected to him somehow, right? He's a chill guy.
Mhm.
He's a very chill guy.
Do you think his predictions will be correct?
I would consider yes.
Okay.
All right. All right. So anyway, let's go back here. So now, what's happening here? Photoelectric effect, right?
Yeah.
Okay. So I think for A, we don't need that information in A, I guess. Uh,
I put another screenshot just for the. There's just a formula.
oh, just a formula. All right then. Hold on. Oh, I just see these new ones. Let's see. One, two. Okay. Uh, okay. Okay, so either way, let's just go through this. Deduce the ratio B to E, wherein B is a magnetic field and an electric field here. They are perpendicular to each other. So only electrons traveling at this speed on the path are undeflected and pass through the aperture. Okay. Um, okay, even though this is photoelectric effect, to start with, it's not actually a photoelectric effect problem. This is a magnetic field and electric field problem. Okay. Okay. Now remember this before we solve this. Okay, remember this. If this were a proton, I'm just okay, I'll just say proton for now. Okay? And then I put it in an electric field going like this. Let's put electric field here, right? Which way is that proton gonna move? If it's moving at a certain velocity v.
Probably downwards.
Actually, it's the other way. It's gonna move up. The electron would move down. Something like that. Okay.
Wait, right. That's so stupid. Okay.
All right. Okay. But let's draw that proton again. But this time, instead of being in going through an electric field, we're now going through a magnetic field. Now, I'm going to just draw the magnetic field the same way for now, pointing up. Okay. And same thing for the V. The V is gonna be like that, right? Which way is it gonna be deflected?
It's gonna go up,
No.
but it goes positive to negative also.
But it's a magnetic field, not electric.
Why would it make a difference?
Okay, remember for electric field, it's pretty straightforward. Those field lines for the electric field tell you which way the charges move. A positive charge would move, right? But for a magnetic field, remember that for a magnetic field, the velocity, the magnetic field, and the force are always perpendicular to each other. Okay? They are always perpendicular to each other. So for this, in this case, this proton here is going to be deflected. Wait. Going to be deflected out of the page. So basically, if I draw this in 3 dimensions, it's gonna kind of look like that in 3D. Okay, but this should be out of the page. All of these would be out of the page. Okay. So okay, let me just see here. Deflected up. I'll just write it. Deflect up. This is deflected out of page. Do you? I just have to ask. Before we continue, there are 2 ways to remember this. IB prefers, no, not prefers, but most sources in that I've seen that go to IB use one way, and most sources that I see for other kinds of examinations like the Cambridge exams or the UK exams or SATs or whatever, they use the other way. Okay? I gotta ask you, did you use the left hand or the right hand to remember the directions for magnetic fields?
Left hand.
Left hand, so that's perfect. Now, The reason why I said that is because I actually personally prefer the left hand to help you remember this, right? I think I've taught you this before, but I'm not sure.
Yeah, but it's electron though. It's
Yeah.
current and it's force.
Actually, no. The current here will still be a positive charge. So in this case, if it were an electron, you just reverse the current, so to
Right.
speak, right? So in this
Yeah.
case, our current here is moving to the right. Okay. So let's go back. Okay. Okay, so our current's going to the right in this case. If this were an electron moving to the right, then the current goes to the left, so to speak. Okay?
Yeah.
All right. Same thing here with this proton. This proton here on the electric field going to the right, the current's going to the right. Okay? But the electron is still, if this were an electron, this would still be going to the left, or rather to the right, but the effect would be on the opposite direction. Okay? So, here's the thing now before we continue. So, if it so happens, what if you put an electric field like this? Okay, that's the electric field. And then I'm gonna draw a magnetic field. This time around, I'm gonna be perpendicular. Gonna be pointing out like this. So that's a magnetic field. Okay? Hold on, this is correct. Hold on, let me see if this is correct, yeah? Yeah, this is correct. So in this case, what we'll do is, the reason why I did these two together is we're gonna put that proton here again. And again, we're gonna stick with the proton. Electron, you just switch the direction the direction, right? Okay.
Yeah.
So in this case, if the proton is moving this way with a velocity v, which way is it gonna be deflected? It's gonna be deflected up by the electric field, but deflected down by the magnetic field, right?
Didn't we say out of the page?
No, in this case, in our example earlier, our magnetic field was pointing up, right? In this example here, the magnetic field is pointing out of the page.
Okay.
Okay, so if the magnetic field here is pointing out of the page, then I'm gonna draw the two forces for now. The electric force is gonna go that way, electric like that, right? Specifically, I'm not gonna draw the path. I'm gonna draw the actual force. The electric force is gonna go that way, and the magnetic force is gonna go down. If you choose the right values for the electric and magnetic fields, these two forces can cancel out. Okay, so
If sorry, if I do what?
if electric and magnetic fields values are chosen properly, um the proton moves in a straight line, right? I'm just gonna
You mean
say it properly.
if they're
Then
the same?
Fe equals Fb, and therefore proton moves in a straight line. Okay. So that's the key idea in this problem. Okay. So now that we have this, and we do have the formulas to find the magnetic force and the magnetic force and the electric force on a charge. We have formulas for it already, right? And one
Yeah.
of those will only depend on V, and that's the magnetic force. The electric
And
force depends only on the charge, right?
yeah.
Okay.
But could we use the left-hand rule to predict the motion in this case?
We could, but we could do that only for the magnetic component, or the magnetic force component. Okay. So the idea here now, if we go to the problem, is there's these undeflected electrons, right? So meaning at this point, the magnetic for these electrons, okay, I'm gonna draw that these electrons have a velocity v0. Okay. Now, if I have a v1 and I have a v2, and they're going to be slower if v1 is greater than smaller, let's do smaller here, v0, and then if v2 is larger than v0, the effect would be this would curve a little bit like so. I'm not really sure which one is which, but definitely they will curve like that. They will have different curves. Okay, only at that perfect speed v0 will it move in a straight line. Okay, all right, so that's the idea. Let's actually look for the answer for b. Okay, now we're gonna involve the equations. So to solve for b, what's gonna be the, again, what's our key idea? That the electric force and the magnetic force should be the same. Oh, sorry, that should be E, right? Okay, and we know that for the force, if you have an electric field, this is just gonna be E times Q. Or well, electron, so charge of the electron is E, right? For the electric
Yeah.
force. For the magnetic force, it's a little bit more complicated than that. Magnetic force, what's the formula? Can't remember from the top of my head. Let me check the data formula, data booklet. From the physics data booklet. Um, but it has something to do with V.
Okay.
BQV. Yeah. All right. I just remember. That's just gonna be BQV. Okay. Now, in case you're wondering where I got that formula, that is basically the same as saying BIL. Okay. But our Q, by the way, is the electron again. So we can see stuff that can cancel out. Right?
Yeah. The
Okay.
E's.
The E's cancel out. So what is B over E? What's B over E? That's just equal to 1 over V. Okay. And is your V given? Your V is indeed given. So from there, you just calculate it. Your V, your V that goes straight is given. Again, other velocities, they will curve and therefore cannot go straight through that aperture. Okay.
But they're all going. All the electrons are going the same speed.
No, that's the thing about the photoelectric effect, right? Some electrons will be faster than others because some electrons will be like coming from a bit deeper from the metal, like maybe a few hundred nanometers below the surface of the metal, and that's enough to make it a little bit slower.
Right.
Okay. Similarly, if you want those electrons coming from somewhere in the middle of the metal, then the ones coming from the surface, they're gonna be traveling too fast. Okay, and it gets selected out.
So the perfect speed is somewhere in the middle. It's not the fastest, but it's not the slowest.
Yeah, that's correct. But we can actually
Okay.
also select it to be, we can get the fastest only, and then every other electron that's too slow will be selected out. Or we could choose the slowest ones, then everything would be too fast, they get selected out as well. So it depends on what you want for the speed that you want. Okay.
And at what point does it curve? For which ones is it?
It
Does
will
the
curve
fast curve?
again. So to interpret this again, so this ratio gives you this speed at which deflection is 0, right? Okay. Now any other speed, um if your B over E does not give you that velocity, that means those other speeds will get deflected. Okay. Other speeds,
Yeah.
other values of V, not V, that 1 over V is not equal to B over E, get deflected. Okay. All right. Deflected. So that's B. That's done. Let's go to C. So the beam of electrons trap no magnetic field. Demonstrate wave nature. There's a graphite sheet and observes concentric rings on a fluorescent detection screen. Um, okay. This is actually just explaining the wave nature of electrons. So why do we have wave-like nature? The first one is diffraction pattern. Okay. It's 3 marks, so we have to hit 3 ideas, right? Diffraction patterns are caused by, are sorry, not caused by, are wave-like properties, right? Okay, wave-like properties. So that's the first mark. Again, I'm kind of doing a hit and miss at this point without the actual marking scheme. So I'm just answering it the way I would do it to get the 3 marks. Okay.
Yeah.
Okay. So the first one is, that's the first one. Diffraction patterns are wave-like properties and not. You can add here not particle-like, right? Okay. Now the second part is um, electrons. The electrons must go through uh, diffraction grating. Okay. So the diffraction grating is provided by the graphite. Okay. Provided by graphites. To be more specific, I'm gonna put this part in bracket because this may or may not be important. Um, Molecular structure. Okay.
Mm-hmm.
Okay. So that's the diffraction grating, and then the third part here is um, so the electrons must have a wavelength corresponding to this size of the diffraction grating. Okay. So electrons pass through the graphite. How to say the third? Pass through graphite, get diffracted, and get diffracted. Because the wavelength of the electron is um, comparable uh, to the size of the graphite molecules or the size of the graphite structures. Okay,
Yeah.
comparable to graphite structure size. That okay. Again, this is me just trying to see what the 3 marks are without the marking scheme. Okay.
Yeah. I'll
Okay.
check it later.
All right. Sure. Um, but either way, whether this gets full marks or not, this is the explanation behind it. Okay.
Okay.
All
Perfect.
right. Great. Um. Okay. Let's see. So that one's done. 15. Okay. Next bit. I think we'll finish on this one and then we'll continue the rest on the next meeting again. Yeah.
Okay.
All right. So the next question here is explain how the pattern of rings would change if the speed of the electron decreased. This time you have to you have to look at the equation for the, what's this, the wavelength. Oops, not current. That should be, okay. So what's the wavelength for something like an electron? What's the de Broglie wavelength? Let's take a look. Something I haven't memorized again. It's been a while. So let's just check it out. De Broglie wavelength, that should be in E. Still F. Okay, de Broglie wavelength, de Broglie wavelength, de Broglie wavelength. Okay, there. The de Broglie wavelength. That actually also works. Remember we used this formula yesterday to find the momentum of an electron, right? This will also work if you want to find the de Broglie wavelength of a particle moving at a certain speed, right?
Hmm.
So in this case,
Okay.
if V increases, what happens to P? Also increases, right?
Yeah.
So what happens to lambda? What happens to the wavelength? It decreases, right?
Wait,
Okay,
but
speed.
V
So
is
it's the other way.
proportional to.
Yeah, it's the other way around. Sorry. So it says here if the speed decreases, right? So let's reverse that. If V decreases, then P also decreases, right? And therefore the
But V
wavelength increases. Go ahead. What you want to ask?
isn't V proportional to lambda? So if V decreases, lambda decreases, so P increases because lambda is disproportional to P.
Uh yeah, that's correct. That's correct. So if P decreases, lambda increases. That's exactly what we have here, right? But the thing is, we don't remember that momentum is equal to mv, mass times velocity. So if you decrease the velocity, and this is a matter particle, so when the velocity decreases, then the momentum will decrease, and therefore the wavelength increases.
Huh. And
Okay.
what if you look at V equals lambda times frequency?
V equals lambda times frequency. That's a different. We can go there. Yeah, I think, yeah, we can also go there. But that means we can just write it down here as well that frequency decreases, right? Actually, no, no, no. Sorry, my mistake. So if you're gonna use it in that equation, let's put it in there. So if um v equals lambda over lambda f, right? Now,
Mm-hmm.
uh, in this case, we cannot use this straight away. This okay. One reason for that is because if you let's see this first. If v decreases, then you say that lambda uh we're not sure whether the frequency changes or not. We're not sure about that. Okay? If we use this straight away. Okay? You get the idea? Because in there's nothing given in our problem that tells us what the frequency is.
So we can't use it just for the sake of proportionality.
No, we cannot. Okay?
Okay.
Now, so yeah, we can't really use this. Okay? So the next thing here is we're now asked not about the wavelength. We're gonna have to go into the idea now for diffraction, right? We know that in diffraction, if we go now into, which one is it? C? Topic C? Yes, it is topic C. So if we go into diffraction, now we will use this formula, theta equals lambda over b. Okay, where b is the width of the slit, right? Okay.
Yeah.
Now in this case, our because we didn't really change anything here for the problem, what in other words, we don't really change anything except the wavelength. So we assume that b is constant, right? We assume this. Now if this were the case, that we can assume this, then from here, if lambda increases, then that means theta increases, right? Okay. Now if theta increases, what happens to the space between the maxima?
It increases.
It also increases. So the pattern of rings will become wider. So ring pattern becomes wider. Widens. Okay, that's it. So that's the answer. That's the full answer going through the whole step-by-step process. Okay.
Great.
Great.
Okay.
Okay. D. Part 1, part 2, part 3, part 4. Oh, we suddenly have relativity in here.
Yeah, it's a crazy mix.
Yeah. All right. This is okay. I think we can go back to this on our next lesson, but I don't want to end right here. I just want to do one of the multiple choice problems you just said. Just one more. Okay. We'll get
Okay,
back to that one tomorrow. Oh, not tomorrow. The next meeting. It's
Tuesday, if it's
Tuesday.
still okay.
Yeah, Tuesday's fine. Okay. So gray body. Oh, okay. This actually, just so you know, I mentioned earlier, I'm in a Facebook group with the DP teachers, with a lot of DP teachers. This problem came up earlier.
Seriously,
Yes,
was
that
there an issue?
not really an issue, but of course, that group has a lot of new teachers in there. So they're asking, how did we get this answer and how, right?
Oh,
Okay.
okay.
So unfortunately for us, though, I don't remember the answer. So let's do this quick.
Okay.
Okay. So here's the idea first. What does it say? Gray body. It's got a temperature T1, emissivity T, and black body temperature T2. The black body is insulated. It doesn't radiate. So the black body will always radiate inwards. Okay. So we have that. The intensity of the radiation by gray body is equal to the intensity it absorbs. This basically means if it radiates, if the radiation going out equals the radiation going in, the temperature is constant. So T1 is constant. Okay.
Yeah.
All right. Then another thing here for the black body, if you think about it this way, let's do it quickly. But the idea here is T1 will radiate and the black body will also radiate, right? And in this case, both of these emissions will be of equal intensity. Okay.
Mm-hmm.
So let's say this is I1 coming out and I2 coming in, right? So this case, I1 equals I2. Now, what's the formula for intensity? We don't really have an exact formula. We have a proportionality. But since we're doing intensities here, we can actually just say that power over area should be equal to power over area. But we have to account for the fact that the middle one is a gray body. So we have to put the emissivity here, right?
Yeah.
Okay. Now, the thing about black body radiation, whether it's black or gray body, um, there is another formula which relates the intensity it goes out with, it emits relative to the temperature. Okay. Let me see if it's in the booklet. It should be under heat, so that should be under B. Let me just double check. No, here, thermal energy, black body with regards to temperature. Okay, here's the thing. Okay, so that's another way of looking at it. Now I'm going to change that P over A into something else again. Okay, just to make it easier, because there is a formula in the data booklet which makes this easier. It's the um let's just put that there, that L is equal to sigma A T to the 4. Okay, this L here is luminosity in stars, right?
Right.
Okay, this can be thought of as intensity as well, because this is exactly the same thing. Okay, so what I'm going to do now is I'm just going to put this into here, that sigma is a constant, the A here is A1, right? And then T1 to the 4. That should be equal to sigma A2 T2 to the 4. What cancels out? The sigma cancels out. We're left with um what's T1 and T2 equal to already? We can kind of guess looking at the equation which one it's gonna be.
Um.
We don't even have to solve it fully.
E- So you have AT and just AT on the other side, so they're gonna be
Mm-hmm.
just affected by the A.
Yeah. So to make it easier, even
So
though we
A.
cannot actually do this, we can assume that A1 equals A2, just to make it easier, right?
Yeah.
Which one's the closest one to do? Add to the
A.
correct answer. It's not
A.
A. It's not A. It's C.
What?
It's
Why?
C because of the to the 4 bit, right? So I'm just gonna write it here again. So if A1 equals A2, right? Then we have E T1 to the 4 equals T2 to the 4. Because of the 4, we take the fourth root, right? So what's the fourth root of
Uh-huh.
the emissivity? That's gonna be E raised to 1/4. T1 equals T2.
Oh, okay. It's only because of the format of the answers.
Yeah, because
But
of this
otherwise,
4, right?
okay.
Okay. So the answer is
Um,
C.
and just one quick question.
Go ahead.
I forgot why we had to put the emissivity sign to account for the gray body.
The gray body, because the emissivity, we actually have to put the emissivity here as well for the black body. So let's label that E1 and E2 here again, right? But for a black body, we know what the value of E is. It's 1.
Yeah, 1.
So that's why it disappears, because it does that 1 there. But technically, we did not
Right.
remove the E2. Okay? Now, so this is going to be the correct way to do it. You put the emissivities for both bodies as well.
Okay.
All right? Okay, I think that's good for today. Anything? You have any questions?
That's it.
All right.
Thank you.
All right. So for Tuesday, we'll meet again, and then let's see what we can finish then. Okay. All right. So we'll end here today
Okay.
if you don't have any more
Perfect.
questions. Okay. So in that case, I'll just see you again next time. You have a good day.
I don't have any questions.
All right. I'll just see you. Good day. Bye bye for now. Thanks for coming.
Have a good day.
All right.
Thank you. Bye bye.
Bye bye now. All right. That's the end of that lesson over there. Yeah. I just hope. Well, for me, I personally, I'm just hoping that people are actually. Well, it's not that they're not interested, but those who find this interesting, because of course it's almost exam season, this is gonna be really helpful. So for those who are actually watching, thank you for watching if you're there. I see another message, but I don't know. The chat doesn't always load. Well, not on OBS anyway. I gotta check it on the stream or... Excuse me. Okay, I'll just make it bigger. Good luck, everyone, for those who are watching. Well, yeah, thank you for that message, Elena. Yeah, good luck. And I do hope, well, if you're still there, I hope you find this useful. So with that, I'll end here for today. But before we do, as usual, don't forget to like, share, and subscribe to the channel. We go live on these platforms. We go live on YouTube, Facebook, and Twitch, and we post every so often in TikTok and Instagram. I'm still trying to fix this right now, but I figured out a way to do it. So whenever there's a new video or a new live video coming up, it will be posted in these platforms and you will be notified. So please just follow them. I'm in the process of testing it right now, and if it works, then it works. Okay. So what else can I say? That's it for now. So also we go live on Twitch if you want to go there. So with that, we'll end here. So I hope you have a good day, good morning, good day, good afternoon, good evening, or good night, wherever you are in the world. Stay freaky, everybody. Bye bye now.